Alright, we continue. This is the second video, so we'll continue on symptoms of multicollinearity. And some of the symptoms which you need to look out for in identifying whether there's a multicollinearity in a model, it's checking the variance of the coefficient of the models. When you have inflated variance of the coefficient, and you should also know that the square root of this variance is what's going to give us the standard error value of the coefficient. So when we have inflated standard error values, it's a symptoms of multicollinearity. Subsequently, when we proceed, by the time we talk about variance inflated factor, really know whether a particular variance of a coefficient is inflated or not. So secondly, we talk about when the R square is large and we say the model is statistically significant. That means when we have the analysis of variance table showing that the model is statistically significant, and also we have our R square to be large. However, when we check the T statistics, that means the significance of each of the coefficient of the dependent variable in the model, we discover that some of the coefficient is not statistically significant. It's also something that we need to bother about, because when we have our R square, say like 0.999, which is trying to tell us that our regression model could able to explain 99% of what is happening in Y, and when we have the F calculated to be greater than F tabulated, in which we will reject the null hypothesis and accept the alternative hypothesis that the model is statistically significant, and having gotten this, we are now having the coefficient of the independent variables, some of them not being significant. It's a contradiction to the result our R square is given and the significances of the model, because when the model entirely says statistically significant, it's expected that every individual member in that model must have contributed and must also be statistically significant. So when we have individual not statistically significant, it's a contradiction, so it's a symptoms also to look out for. Thirdly, when we have to remove or add one predictor variable, and the result in the result of what we are going to have after adding or removing, we have a result that is largely different from what we have initially. So what are we talking about? We already have our data. You've analyzed the data, the model has been set up. After setting up the model, probably we decided to remove a particular variable from the model, or to add a particular additional variable to the model. And after doing whether the removing or the addition, we find out that the result which we have after adding or removing, it's largely different from the initial result before we had the remove. Then it also suggests a multicollinearity problem. Or fourthly, when we have the correlation coefficient R of a variable indicated to be positive correlated with Y, however, the coefficient of that variable is negative value, this is when we have a bizarre beta weight. What are we talking about? We look at the correlation matrix or the correlation value between a particular X and the Y, and we find out that there is a positive strong correlation, or once it's positive, there's positive correlation with Y. That particular independent variable is having positive correlation with Y. But by the time we did the estimation for the parameters, the particular parameter of X that has positive correlation with Y now has a negative value. It's a contradiction, because if it has a positive correlation, it means as that X increase, we expect the Y also to increase. Now to see a negative value of beta for such independent variable, it's a contradiction. So when we have situation like this, it's also a suggestion, a symptoms to a multicollinearity problem. Also, when we have a large confidence interval, and it's a big problem, the confidence interval is so large, it's also a symptoms of multicollinearity. So let's look at the effects of multicollinearity on a regression analysis. The prominent effect which we need to look at first is when we have a wider confidence intervals, and this will bring about a less reliable p-value. The confidence interval is so large, so this will result in a less reliable p-value for the independent variable t-test, and this will make us not to have some of the independent variable tests not to be statistically significant. What are we talking about? What are we talking about here? It's a situation where we have our standard error of the coefficient being inflated. That means this is becomes inflated, it becomes large than what is expected of it. And by the time we are calculating our t, we are estimating our t calculated for our t statistics, you find out that no matter the value of the beta, coefficient of beta we have here, since this is being inflated as a denominator, this value will always be small. And once this value is small, the t calculated in comparison to the t tabulated, we're going to end up accepting our null hypothesis that the particular coefficient is equal to 0. That means it's not statistically significant, and this has to do with the problem of having an inflated standard error, which is caused by the multicollinearity problem, and this makes our p-value to be less reliable. So this problem also is what leads to what we say, that it is harder to reject null hypothesis, since this will always become smaller than what is supposed to be, because the standard error is larger than what is truly expected to be. It is inflated, so it's going to be harder for us to reject the null hypothesis. And this also can lead to skewness or misleading inference result. And also, the effect for we could also talk about is that we can no longer make inference on the unique effect of individual y, individual x on y, as we